So let us start, right? So we will be discussing about the standing waves, right? Right? Standing waves. So the concept of standing waves is in one particular thread, if there are two different waves that are traveling in the opposite direction, suppose there is one wave actually that is traveling in this direction, and there is one more wave which is traveling opposite direction like this. Then actually you can see actually when you continuously give the jerks to a thread like this, so you are keep on giving the jerks. Then actually you can notice that actually there is such kind of, this is the 8 actually, 8 is the symbol actually you can notice, which is horizontal 8. And this kind of scenario is called as the standing wave. So this is called as the standing wave. Now why we have to call this as standing wave? That you need to understand one important aspect. That is, the first thing is why we have to call this standing wave is, standing means static. That means there is no movement. We are calling this particular wave as the standing wave because there is no transfer of energy. Or the wave is not non-propagated wave. So in this particular case actually you can notice that non-propagated wave, earlier actually we have discussed one scenario. If there is one wave actually that is traveling in this direction, now what exactly is traveling is the jerk what was given to this particle here, that is transmitted to the very next particle, and that is transmitted to the very next particle like this, and this jerk actually keeps on travels and then actually it moves on in this particular direction, right? So this is actually the energy or the disturbance, it is traveling from here to here, and this is a traveling wave. So this is called as a traveling wave. And in this particular case, the disturbance actually whatever is doing in this direction, there is exactly in the opposite direction also there will be a counter disturbance which is coming back to the exactly the same position. Hence actually the particle whatever is going to be here, the energy whatever it gives to the adjacent particle, it is taken back again. Hence actually the energy which is going in this direction, it is coming back in the opposite direction. Essentially there is no effective energy transfer from point A to point B. So this is point A and point B. Now in this case actually the scenario is treated as the standing wave. Now if you notice the equation of the wave, actually the traveling wave, we have derived the equation as A into sine of kx minus omega t plus phi, and this is the case where we treat this wave as the traveling wave. And the traveling wave actually, the velocity of the wave energy we have calculated by making this kx minus omega t plus phi is equal to a constant. Hence actually k into dx by dt minus omega equal to 0. From this actually we have derived that the velocity of the wave dx by dt is equal to omega by k. This is f lambda, right? And this we have derived it. Now in the case of the standing wave, the wave which is traveling towards the positive x direction, this is the velocity in the positive x direction, that is positive dx by dt is equal to omega by k. So this is a positive velocity. Suppose if this happened to be kx minus omega plus omega t plus phi equal to constant. Now the derivative of this is going to be of exactly in the opposite direction. Hence this is going to be of minus omega by k, or this is minus f lambda. So this is the case of the wave energy that is traveling in the opposite direction. So this particular scenario, if you talk about, there are two different waves. One wave which is traveling in this direction, this is the first wave, is given by y is equal to, so A into sine of kx minus omega t plus phi. So this is traveling in the positive x direction. And there is one more wave which is initiated here, and then actually it is traveling in the opposite direction. And this wave is, so this if you call as y1, and this is y2, A into sine of kx plus omega t plus phi. So this is traveling in the opposite direction. Now as there is a wave traveling in the positive direction and there is a wave traveling in the opposite direction, as per the principle of superposition, the combined effect at any instant is going to be the sum of both y1 and y2 together. So, as per the principle of superposition, y is equal to y1 plus y2, and hence actually y is equal to a into sine of kx minus omega t. I treat phi equal to 0 for the simpler analysis purpose. And the second one is a into sine of kx plus omega t. So this is the wave traveling in the negative x direction, this is in the positive x direction. And the sum of this is going to be of a into, so sine c plus sine d, so that is 2 sine c plus d by 2. So kx plus kx by 2. Because kx minus omega t, kx plus omega t will be cancelled out, and then cos of kx minus omega t minus kx minus omega t by 2. This kx will cancel out, and then we left with 2a times of sine of kx cos of omega t. And this is the equation of this standing wave. Now, if you notice, the kx and omega t are separated out, and hence actually you cannot find a direct relation between these two, obviously. So kx minus omega t we equated to a constant, and we derived the velocity of the wave. Now, in this actually it is completely separated. Now, this actually one of the very important equation of this standing wave. This gives a lot of information for us. So let us take this particular scenario. And then actually, so let us say this is the wave. And then actually in the counter direction, there is one more wave like this. Now, the amplitude of the wave at any instant, if you notice, this is kx actually within this sign. Now this entire thing, so x is nothing but the displacement from the initial position. So this is the initial position, and this is at a length of x. So it is at a length of x. If you notice, the maximum amplitude is going to be decided by the displacement from the origin. So that means sine of kx value, if you notice, this is the maximum value, and then the particle of the string at this particular point is always deviated for the maximum value on either sides. And here actually it is deviated for a smaller value than the maximum value. And here also actually it is deviated for a smaller value than the maximum value, which means that this particle is undergoing the simple harmonic motion, and the amplitude or the maximum amplitude of that particular place is going to be given by 2a times of sine of kx. So the amplitude at this particular point is 2a sine kx. So this is a1 if I call this, and this x is actually displacement. So let us say this is only 1 centimeter. You will be putting 1 centimeter in this x value, and that will be the entire displacement or the maximum displacement that can occur at this particular position. And this omega t is corresponding to the period of the oscillation, and every particle will be having different displacements or different maximum amplitudes, but it will be having the same frequency. So that means the particle whichever is located here going to till this particular point and coming back to this position and going in the downward direction and again coming back to the same position. Let us say it took a time of 1 second, but the particle here, this is going to the maximum possible distance and coming back to the 0, and then it is going to the maximum negative distance and coming back to the 0. And this particle also, to complete one cycle, it again takes 1 second. Now if I take particle here, then actually even here also, though it is very small displacement, but still it takes 1 second. So at every point, the particle is oscillated with different amplitudes, but of same frequency. This is very important to understand. So every particle is having a different amplitudes, but it is oscillating with a single period of motion.